Hope you are doing well with virus disease. Before going to the next chapter, let me make an very briefly overview on what we have learned about. In chapter 1, we have learned about the plasticity of the material, and beyond that, the idealized curve is introduced. Then in plastic analysis and design, we use the idealized curve. And we also have learned about the plastic analysis, and it is different with elastic analysis. Then we also have introduced about the plastic hinge and different design format has also been introduced. In chapter 2, plastic hinge length has been introduced. Then chapter 2 also focused on the plastic moment capacity or plastic capacity of the section. And the important thing is the effect of the action force, shear force, or local buckling on the plastic strength of the section has also been discussed about. Okay, so in this chapter, chapter 3, we are going to learn about the different tools used in plastic analysis and design. Okay, so this chapter focus on the tools used in plastic analysis and design. So I think it is very important concept and procedure. First of all, let me make an introduction on these specific problems. First, we will talk about the exact solution. As you already know, in elastic analysis, we use the equilibrium equation or compatibility equation, and also elastic moment. And elastic moment is a function of stiffness and curvature. Okay, then you are familiar with elastic analysis. In plastic analysis, we also use equilibrium equation. But the difference is we use the mechanism condition. Okay, mechanism condition. I will explain this concept. Okay, but we use mechanism equation or mechanism condition. And in plastic analysis, we use plastic moment, MP. Plastic moment, as you already know, MP equal to the G multiplied by sigma y, and G is the plastic section modulus, and sigma y is depend on the material, strength of the material. Problem is that the exact solution can be used for the simple structure, okay, but in a complicated structure, for example a frame, then we may have problems. We cannot, in another word, we cannot use the exact solution for the complex structure because it is too complicated for using the exact solution. Okay, So it leads to an requirement of an approximate solution for hand calculation of a complex structure. Okay, do you understand? Because the exact solution is not easy, or it cannot be used for a complex structure like a frame. Then it needs a approximate solution for hand calculation of a complex structure. So that's why we need a new tools. Okay, we need a new tools, not a exact solution. So in this chapter, a new tool will be introduced. That is virtual work method. Okay, virtual work method. And it is new concept. I think a new concept for you, but don't worry about. I'm going to talk about that. I will explain what is a virtual work method and how to use these tools for plastic analysis and design. Okay. And second, to use this method, we need some new assumptions. Okay, new assumption. For simple plastic analysis and design, two basic assumptions will be used. Okay, the first assumption is large deformation. Large deformation is due to ductility of the material. Okay, so it means the structure is assumed to exhibit with a large deformation of a section. Okay, of a section. The section is exhibit with a large deformation. So by using this assumption, the plastic moment or plastic strength of the section can be observed. Okay, so if we use more deformation, then we cannot obtain the fully plastic strength of the section, especially fully plastic moment. Okay, and the second assumption is the small deflections. Small deflection means the small deflection of system. Okay, for geometry does not change. Okay, so we assume the geometry of the structure, whole structure does not change. So small deflection means system, for structure. Large deformation means for section. Okay, so this is for section, and this assumption is for the whole structure. In the whole structure, we assume the deflection is small enough to maintain the shape of structure or the relation between the displacement and the force. Okay, to maintain that relationship. So that is two assumptions. Ductility requirement. We have two requirements for the ductility. The first requirement is for plastification. Okay. For plastification, it is a section member. Okay, a section member. It means to obtain the full plastic moment capacity. Okay, full plastic moment capacity of the section. To obtain that, in theoretical, fully plastic moment is obtained only if the stem fibers are capable of sustaining the yield stress up to infinite strength. That is theoretical. Okay, theoretical. Actually, it is idealized concept. Okay, idealized concept. The stem fiber are maybe not capable of sustaining the yield stress up to infinite strength. So, but in practical, it has been proved that 99% of fully plastic moment capacity can be obtained. That is good news, right? So 99%, not 100% theoretical, but 99% of fully plastic moment capacity can be obtained. But with the requirement. The requirement for 99% of fully plastic moment capacity is the rotation capacity of about 2 to 8 times of elastic rotation capacity. What does it mean? Okay, I will explain. This is a moment curvature curve. Okay, moment and curvature curve. We already learned about this one. Let's say here is for I section and it is for the type of section, diamond section, something like that. Then this is the elastic rotation capacity because this part is elastic. Okay, then this is elastic rotation capacity, and it's in practical it's required that for 99% of fully plastic moment capacity, the rotation of structure of section, okay, of section should be maybe about 2 to 8 times. So maybe here 2 to 8 times, or here to here. So this part is rotation capacity due to the ductility of the material. Okay, so in another word, the fully plastic moment capacity can be obtained if the rotation capacity of about at least 2 and to maybe 8 times of elastic rotation capacity. That is a requirement for plastification or for a section. Okay, for a section. For a system, the ductility requirement is for structure or for system, okay, it's required to form the failure mechanism. Okay, to form the mechanism, it's required that. So in LRFD guideline, it is required that to form the failure mechanism to ensure that the system form the failure mechanism. Then LIFD require first the local buckling. With the local buckling, lambda should be smaller than lambda p. Okay, then it is lambda is width to thickness ratio. I already introduced this. Then shortly, it's required that lambda should be smaller than lambda p. Okay, so in this analysis, to apply this analysis method. Then we assume a local buckling should be smaller than lambda p. Lambda smaller than lambda p. With the lateral torsional buckling, L should be smaller than LPD. Here L is length of the structure, okay, of the component. For example, we have column, okay, then this is effect length of the column. So effect length of the column, okay. For example, like this. It is a simple column, and its length. If the column has another boundary condition, then we have to calculate, we have to determine the effectiveness length. It is L, okay. And this L should be smaller than LPD. That is we call unbraced length. Then this value can be calculated by using a given equation. And I will talk about the equation later, okay? But just understand that we have a given length, unbraced length, a requirement, and effectiveness length should be smaller than that specific value. And then okay, so we have two requirements. The first requirement is for section, okay, for section, and the second is for system. Alternatively, it's based on the rotation capacity. So they found that the rotation capacity may be equal 3 or greater. So greater or equal 3 times of elastic rotation capacity for non-seismic area, and rotation capacity, plastic rotation capacity, greater than or equal to 7 to 8 times of elastic capacity, rotation capacity for seismic area. Okay, that is a requirement. Okay, so we just assume requirement is meet, and then we can do the elastic analysis using Newton. One more concept is mechanism. Have you ever heard about this concept, mechanism? What is mechanism? Have you ever heard about mechanism? Okay, I will explain a little bit. For example, if we have a simple beam under concentrated load at the middle, then can you determine the failure shape of this structure? The collapse assumption. Okay, what is collapse assumption? So with this structure, we can assume with different collapse. Okay, for example, this is the one assumption. We assume that if this beam is collapsed, if the hinge, plastic hinge, occur at the middle at this point, and it's collapsed. Okay, so we call it is mechanism. And this is one of the different assumptions okay, or it means one of different mechanism. So this is mechanism. Mechanism. So we can understand that mechanism is a collapse assumption, something. And actually, we can assume different assumption. For example, we assume the mechanism like this. So let's say this is mechanism number 2. Actually, because it is very simple structure, then we know that is wrong mechanism. It's not right mechanism. Maybe here, this one is good mechanism, right? Because it is exact mechanism. We know because it is very simple structure. And here is wrong mechanism. But in concept, you can assume with different mechanism. Okay, in some in structure in system, in a complicated problem like a frame, sometimes we don't know, we cannot determine the correct mechanism. That's why different mechanism is important. We can assume different mechanism, just assume, and then we check using some tool that I am going to talk about later. But in this case, you should understand what we need different mechanism. Okay, so uh, anyway, we need to assume different mechanism. So, for example, we can assume other mechanism like this. It's freely to assume. Maybe it's wrong, right? But we will check later. But maybe it's from here, from somewhere. But that is we call mechanism. Okay. So, for example, here mechanism number 3. Okay. So in a short word, for a structure, we can assume different mechanism. And problem is that you understand the concept mechanism. Okay, mechanism maybe means uh, that is collapse assumption. Okay, that is core mechanism. Then in a structure, one system, you can assume different mechanism. Okay, if you assume a correct mechanism, then we can check and find out that it is correct mechanism. If we assume with wrong mechanism, then we may face with some problems. Then we can check later. Okay. However, I hope that you understand the concept of mechanism now. So from now on, I just mention mechanism, and I assume you understand what is mechanism mean. Okay, what is mechanism mean? One more concept is virtual work. Virtual work. Virtual work is very powerful concept, powerful tool, powerful method, which is used for plastic analysis. Okay, so from now on, we will use virtual work. That is main tools for plastic analysis. The concept is very simple. Okay, concept is simple. It is external work should be equal to internal work. Very simple. Okay, so for virtual work, we have to calculate external work and calculate external work. Then external work should be equal to internal work. So this is main condition of virtual work approach. Then in next step, I will talk more detail about the concept of virtual work and how to apply the virtual work approach in plastic analysis. Okay.